Welcome everyone to the 35th meeting of New Directions in Group Theory and Triangulated Categories. Today we have Antonio Lorenzin from Milano-Bicocca and Pavia, and he will talk to us about formality and strongly unique announcements.
Okay, so thanks to Roderick for the possibility. I hope I've pronounced it correctly or almost correctly. Okay, thank you. And so today I will talk about formality and strongly unique announcements. So the idea is, first of all, of giving an idea of algebraic triangulated categories, which is done via DG-categories. Then we will move on to the motivating example to study stronger formality, which is just a wider definition for intrinsic formality for those of you who know what intrinsic formality is. If you don't know it, it's not a problem. I will also define that. Afterwards, we will have the definition of strong formality and we will be able to go to the main result. And at the end, I will talk about application to the bounded homotopy category of complexes and the bounded derived categories. So first of all, let me say that for me, everything will be k-linear, where k is a commutative ring. And I should also say we are working in an appropriate Grothendieck universe, U, and everything is considered to be U small. So moving on to the preliminaries, I want to recall that a chain complex is a graded module with a differential, meaning that for every integer, we have a module, and then we have these connecting morphisms, and the composition of two of them will give 0. Now, a DG category is simply a category enriched in chain complexes of K modules, meaning that the morphisms between two objects are a chain complex, and the composition is just a morphism between the tensor product to the targets of the composed maps. And of course, this should respect the degree and the differential. The important part is the homotopy category, as we will see, which is H0 of C, and it has the same objects, but now the morphisms are just the homology at 0. And of course, we can do the same thing for graded homotopy category, which is just considering all homology modules. The important part is that on a DG category, we can define the DG version of shifts and cones of the triangulated categories. And in this setting, they become functorial. So we are very, very happy. And so now we can simply say that a pretriangulated DG category is a DG category closed under DG cones and DG shifts. And of course, under these assumptions, one can see that H0 of C is a triangulated category using the DG notions. An important thing to know is that if we consider a DG category, we can always close it and consider the pretriangulated closure denoted with the C pretre, and this is determined uniquely up to DG equivalence. I will say what a DG functor is, but you can imagine this is the equivalence we want. And now I will denote with TR of C the triangulated category associated to C, which is the homotopy category of its pretriangulated closure. Just to give you an illustration that I have in mind when I think about this thing, even though it's not really great, the idea is that you have your DG category, which can do whatever, and then the pretriangulated closure is something similar to a cylinder because you have shifts going up and down, and of course you also have this closure using cones. This is not really a good illustration, but I think it may help you understanding the situation, because the idea is that you are dealing with something that has more dimensions than the triangulated category on morphisms, of course. And when we use this map, we can see that the homotopy category is, of course, contained in the triangulated category associated. So what is a DG functor? A DG functor is just a functor between DG categories, and we require that the morphisms between home sets they respect the DG structure. So they are morphisms of degree 0 commuting with the differential. Another important thing is that if we have a DG functor between two DG categories, then we can extend it uniquely to the pretriangulated closure. Moreover, if we have a DG functor f between pretriangulated categories, H0 of f is a triangulated functor. And this, well, comes directly from the definition of the cones and the shifts in the DG world. So now we are able to say what a DG enhancement is. And a DG enhancement is simply a couple, CE, where C is a pretriangulated DG category, and E is a triangulated equivalence between the homotopy category of our DG category and T, the triangulated category we wanted the enhancement for. So now what we can say is that if T admits a DG enhancement, then it is algebraic. So the idea is that, roughly speaking, we can restore functoriality when dealing with algebraic triangulated categories. But now a question arises, and is, can we do it in a unique way? Can we find this cylinder that I showed you before in a unique way? And what does it mean to have it uniquely? This is the notion of uniqueness of enhancement. First of all, we need to describe what a quasi-equivalence is. So a DG functor between pretriangulated DG categories, F from C to D, is a quasi-equivalence if just the homotopy functor associated is a triangulated equivalence. And now we just say that an algebraic triangulated category T has a unique DG enhancement. If given two enhancements CE and C prime, we can find a zigzag of quasi-equivalences. So moving from C to C prime. And this is all for the preliminaries. Now we can move on to strong formality. And we talk about the motivating example to study strong formality before giving the definition. So let, first of all, K be a field, and then we can consider the category of finite dimensional vector spaces, K mod. K mod can be equipped with a triangulated structure, and this structure is simply given by the shift between the identity and the distinguished triangles to be described by the short exact sequences of vector spaces. So now there's a theorem by Schlichting telling us that if we consider K to be the field with P elements and P a prime number, okay, then K has two enhancements. And these enhancements are associated to Z over P squared Z and FP of FP epsilon over epsilon squared. And in a sense, one can see that these two rings gives us two enhancements. And now we can also show that there is not a zigzag of quasi-equivalence between them. So in particular, K mod does not have a unique enhancement. The important thing to notice is that the enhancement associated to Z over P squared Z is Z linear, but it's not FP linear. So now the question is, what about uniqueness of enhancements for K linearity? In order to address this question, we talk about intrinsic formality. So first of all, I will say what formal is, and then we will define intrinsic formality. So let A be a DG ring. If you don't know what a DG ring is, just think about a DG category with one object. Then A is called formal if there exists a zigzag of quasi-isomorphisms, moving A to its graded homotopy, or I should say graded homology in this case. Okay, so first of all, there's a question. K has to be a field here because for this to have a triangulated structure, we need the category we are starting with to be split. And this follows because triangulated categories, if you have a monomorphism, that is also split. So you should have some very, very nice ring, I should say. You can also work with some rings. Don't worry, I always ask silly questions. So, okay. What is a quasi-isomorphism? Well, a quasi-isomorphism is a morphism preserving the graded homotopy. So we are moving from our DG ring to other DG rings, and they all have the same graded homotopy. So now what we say is that a graded ring B is intrinsically formal if any DG ring A, such that they have as graded a homotopy B. Well, every DG ring like this is formal. So the idea is that we can always construct this quasi-isomorphism for every DG ring we are working with. This is very, very similar to uniqueness of enhancements. So now what we do is consider any enhancement, consider any enhancement CE of K mod. And now if we pick A in C going to K, we can see that its graded homotopy is KT-1 with T of degree 1. This can be shown simply because the shifts are the identity. And so our idea is to prove that KT-1 is intrinsically formal, because in that case, we will have that the enhancement is unique simply by considering the zigzag offered by the formality. So we can move via the extended version of two pretriangulated closures, and we can move obtaining quasi-equivalences, and the inclusion of A in C gives another quasi-equivalence. In fact, we can definitely prove that KT-1 is intrinsically formal, so K mod has a unique K-linear enhancement. Also, let me point out that we know that KT-1 is not intrinsically formal if we consider linearity over Z by the theorem of Schlichting, because at that point, we will have different enhancements. Yes, A1 and A2, they are the DG rings we have defined, we have here, okay? And they are just part of the quasi-isomorphism, the zigzag of quasi-isomorphism, because we are moving between DG rings with the same graded homotopy. Okay. So now that we have this proposition, we wonder if this is something really related to KT-1, or if we can work for every intrinsically formal graded ring. And actually, the same procedure gives us uniqueness of enhancements for intrinsically formal graded rings. So we can state something more strong, which is the following. If we consider an intrinsically formal graded ring, then for every enhancement CE of the R of B, we have a zigzag of quasi-equivalences moving from the pretriangulated closure of B to C. And this is done in a way that we are fixing B, or I should say, it's not B we are fixing, but the only object that B has as a DG category. Okay. Also, let me point out that a graded ring for us can be a DG category with one object, and the differential in this case is 0. And now, in the same fashion of this proposition, we simply say that a DG category A is strongly formal if for every enhancement C of the R of A, we have a zigzag of quasi-equivalence F from the pretriangulated closure of A to our pretriangulated DG category given by the enhancement. And this actually fixes all the objects in A. Roughly speaking, strongly formal categories are fixed at the homotopy level because we have just fixed all the objects inside of it for every enhancement we can think of. Also, it follows that if A is strongly formal, we have that the R of A, the triangulated category associated to A, as a unique enhancement. And this simply follows from definition. And we also have this other thing, meaning that the pretriangulated closure of A is strongly formal if and only if the triangulated category associated to A as a semi-strongly unique enhancement. I haven't defined semi-strongly unique enhancement. I will define it in a moment. But what I want you to think about is that strongly formal permits us to move between uniqueness of enhancement and semi-strongly uniqueness of enhancements. So we have this property that actually give us a range of moving between the two. So now, what is semi-strongly unique enhancement and what is strongly unique enhancement? We consider an algebraic triangulated category. We say T. We say that it has a strongly unique enhancement if for every two enhancements C and C prime prime, we can find a zigzag of quasi-equivalences F, such that this diagram commutes up to natural isomorphism. And when we ask for semi-strongly uniqueness, we are doing this just for the objects. So as you see, this property is very, very near the one we have used to describe strong formality. Okay, something about the theory. We have many questions regarding enhancements. First of all, we have the question if there is a non-algebraic triangulated category. And the answer to this question is yes. There is a work by Muro, Schwed, and Strickland showing a non-algebraic triangulated category. And we actually have also example of non-algebraic triangulated categories when we require linearity over a field. Actually, we have one example, and that is done by Rizzardo and Van der Berg. So now we can move on to another question. Are there algebraic triangulated categories with a non-unique enhancement? And the answer is still yes, because we have shown it. The category of vector spaces, finitely dimensional, but actually also of all vector spaces, is an example when we consider the triangulated structure described in the previous slides. And so now we should wonder, are there algebraic triangulated categories having a unique enhancement, but not a strongly unique enhancement? And the answer to this question is we do not know. So we would like to see if it is possible to find such an example. I actually haven't found an example. I haven't even proved that this never works. But I am motivated by this question, and I wanted to understand how we can work from unique enhancement to get strongly unique enhancement. So the idea was, can we find some property to characterize strongly unique enhancements for the triangulated category associated to A when A is a DG category which is strongly formal. This characterization can, of course, be used maybe to answer this question, but at the moment, we do not know. So in order to move to our main result, we need another definition. Let us consider a DG category A, and then consider a triangulated equivalence, F eta, between the triangulated category associated to A. And now we fix all the objects in the homotopy category of A. What we can do is that we can define a graded restriction. It is a restriction because we are restricting only to A, and it is graded because we are considering the graded homotopy, not only H0. And this graded restriction is defined here. I hope not to scare you. So on objects, they are, this is just the identity, because we have asked for F to fix the objects. Now this functor also fixes the objects. While on morphisms, what we do is we move with F, and then we use eta to go from the application of F to Y shifted, going to Fy shifted. So we can go to A as well, because F of Y is actually Y for our requirement above. So now what we say is that a DG category A is formally standard if given any two autoequivalences fixing A, and also they have a natural isomorphism between the graded restrictions, then we can find a natural isomorphism between the two functors. Roughly speaking, formally standard categories fix the homotopy level. If you recall what we said, roughly speaking, about strongly formal categories, well, they are fixed at the homotopy level. So now the idea is that if we combine both of them, we should have that the homotopy level and the DG level behave accordingly. We should get this. But of course, this not always works. In order for it to work, we need to go.
Antonio, can I ask a silly question myself? Can you go back to this last slide? So this result of strongly formal categories being fixed at the homotopy level, this is your result?
This is something like roughly speaking.
And this is new, right?
Yes, I mean, there are things in the theory that suggest this, maybe, but no one has really pointed it out. Strongly formal categories are a definition I introduced in order to understand better what happens. So this is new as a definition, but I think the idea is already in the theory in some sense.
Yeah, because formally standard categories being fixed at the homotopy level, I think that one was known. But I mean, from your definition of strongly formal, it didn't seem obvious or, let's say, trivial to me that strongly formal being fixed at the homotopy level would follow from formal being fixed at the formal standard being fixed at the homotopy level. Sorry. Okay. Sorry.
Yeah. Don't worry. I should also say that formally standard and strongly formal are, how to say, they are very different, and they give us two different perspectives of the categories. Okay, so we should not expect a strongly formal category to always be formally standard, but of course, we do not know this because we do not have an example of a triangulated category having a unique enhancement and not a strongly unique enhancement. So now the theorem I proved is that if we consider B to be a graded category, so a category whose DG category whose differential is 0, then we have that the following are equivalent. So B is strongly formal and formally standard if and only if the triangulated category of B associated to B as a strongly unique enhancement. What's new about this result is that the theory was focused on proving results for linearity over a field and in very specific cases. But this theorem holds for any K-linear graded category, and K, I would like to remind you, is just any commutative ring. So if you think about Z, you have just graded categories. Okay, so now some little applications. If you consider R to be a semi-simple ring, then TR of R has a strongly unique enhancement. If R is any ring, then we should see whether R is simply formally standard, because we have a very, very known result saying that any graded ring concentrated in degree 0, which is any ring, is always intrinsically formal. So we have a strong formality for free. It becomes rather tricky for this when we consider real graded rings. But in the case of K mod, the category of finite dimensional vector spaces, well, we have a strongly unique enhancement when we consider K linearity. And as I mentioned before, the result by Schlichting in fact shows also that Fp of T(t)-1, where Fp is the field with P elements and P a prime, is not intrinsically formal as a Z linear graded ring. Actually, for K mod to have a strongly unique enhancement, this is very, very natural once we prove that it has a unique enhancement, because everything is kind of trivial, and once we have a functor fixed in K, we have everything works nicely. So what about meaningful applications? Because these are not really so meaningful. In order to talk about meaningful applications, we will move to the bounded homotopy category of complexes and the derived categories. First of all, let me state some notions which are given by Xiaogu Chen and Yu Ye. We say that an additive category A is K-standard if for every triangulated autoequivalence F on the bounded homotopy category of complexes of A, we have that whenever F of A is contained in A and we have a natural isomorphism between the restriction of A to the identity of A, then we can extend it to a natural isomorphism between F and the identity on the whole triangulated category. In the same fashion, if we have an abelian category A, we can say that it is the standard if the same property holds for every triangulated autoequivalence F on the derived category associated to A. Okay, let me get a sip of water. So now we should ask if these properties are actually similar to formal standardness, the one I described above. And in fact, what we can prove is that K-standardness and D-standardness are very specialized versions of formally standardness, meaning that an additive category A is K-standard if and only if it is formally standard. And this is true because if we consider the triangulated category associated to an additive one, which is graded concentrated in degree 0, then we get exactly KB of A, the bounded homotopy category of complexes. And this holds for all additive categories. For the standardness, the situation is a little bit, for the standardness, the situation is a little bit different, but we still have that the standard is something like formally standardness, but we have to move to a certain associated DG category. So we cannot work with A because the R of A will be the bounded homotopy category of complexes, and we want to study the derived one. So now, since the R of A is equal to the bounded derived category of the bounded homotopy category of complexes, we actually obtain the bounded homotopy category of complexes as a semi-strongly unique enhancement. This has never been stated before, but in fact, it follows immediately from a previous result of Lorenzin and Orlov, who proved that TR of A as a unique enhancement, but they didn't notice or they didn't say explicitly that that is simply the bounded homotopy category of complexes. So since we have this, actually we have that A is strongly formal. So as one should expect, we have that an additive category A is K-standard if and only if the bounded homotopy category of complexes over A as a strongly unique enhancement. And this simply follows by the main result, because as I was saying, since the R of A as a semi-strongly unique enhancement, we have that A is strongly formal. And the K-standardness is just formal standardness. So we are just using the theorem. The situation of bounded derived categories is different, but thanks to Canonical, Niemann, and Stellari, an article from 2021, we have that this category as a semi-strongly unique enhancement for all abelian categories. So now the machinery still works, and we can prove that an abelian category A is, if an abelian category A is the standard, then the bounded derived category of A as a strongly unique enhancement. And this holds in the generality of K-linear categories, where K is a commutative ring. One should ask maybe if we can reverse the arrow, and I do not know general result for this, but I have proved that if the bounded derived category of A is very nice, then we have that this is an if and only if. So from this corollary, what we obtain is that if A is hereditary, meaning that the X groups are all trivial for n greater than 1, then we immediately have that the bounded derived category of A as a strongly unique enhancement. And this follows because Chen and Ye actually proved that every hereditary abelian category is the standard. So we can use this corollary to prove that the bounded derived category of A as a strongly unique enhancement. If you want an example of a hereditary category, well, you can just think about finitely generated Z modules. So you have this example for strongly unique enhancements. Another very, very interesting result that I like is the following. Let A be an abelian category with enough projectives, and consider proj of A the subcategory of projective objects. What we can prove is that if the bounded homotopy category of complexes over the projectives objects as a strongly unique enhancement, then the bounded derived category of A as a strongly unique enhancement. And this still follows from our result of Chen and Ye by using our corollaries linking standardness and strongly unique enhancements. And I also would like to point out that this category is not equivalent to this one. And in fact, in general, it is very, very hard to move from categories that are not equivalent and having still this strongly unique enhancement. Because if you pick a triangulated category, which has a strongly unique enhancement, it is not said that a triangulated subcategory will have a strongly unique enhancement. You cannot move via inclusion, you cannot move via quotients, you can never move with this property. To conclude, I would like to talk about the geometric cases, what has been done in the theory till now. Now let me talk about the bounded derived category of coherent sheaves over X. And now this has a strongly unique enhancement if X is a projective variety over a field whose maximal torsion subshift T0 of the structure shift of dimension 0 is trivial. And this is a result by Luntz and Orlov. If you don't know what this property means, you can just think about smooth projective varieties. Actually, it has also been proven that we can do the same thing if X is smooth and proper of dimension greater or equal than 1 over a field. And this is a result by Hollander. The interesting part about these proofs of strongly unique enhancements is that they first show the standardness. They have to go through the notion of the standardness. So, in fact, we are able to extend the generality in which these methods, the methods used in both of these proofs, can be used. In order to do so, let me remind a definition given by Canonico and Stellari. Actually, here I will not give their definition, but a definition that is equivalent. So if we consider an abelian category A and a set I, we can consider Pi with I becoming the index set of this collection of objects. And now this is called a quasi-ample set if for any I, we can find some indexes and we can find some natural numbers such that we have an epimorphism going from this direct sum and we cannot go back. So I would like to think, I like to think about these properties as we can surject on all objects, but we cannot go back. And well, the first property also in many cases, but the other one, the condition 2, is very hard to understand and to prove. And I should say it's the one giving problems. But we need both in order to prove that if an abelian category A admits a quasi-ample set, then we have the bounded derived category of A as a strongly unique enhancement. And well, that's all. Thank you for your attention. If you have any any questions, sorry, please feel free to ask them. And these are some references.
Thank you, Antonio. Can we all unmute ourselves and give Antonio a round of applause? I have one question, but I'll wait to see if anyone else wants to ask something. So there is a question in the chat, but I think by mistake, the question has been sent personally to me and not to everyone.
Oh.
So I'll just ask it on Tom's behalf. So if you can you go back, actually I thought about this as well. So can you go back to that slide where you introduced bounded derived categories for the first time? Like the back. Yeah. So go forward.
Here.
Yeah. No, go back.
This one?
So yes, so no. I mean there was a corollary to the Canonico-Niemann Stellari result.
Yes.
Yes, you said here, I mean, this is the question, that for nice enough derived categories, this is an equivalence. You said that, right?
Yes.
Yeah. Can you expand on nice enough?
Yes. Well, it is a really strange property. I should say that, of course, we are working with K-linear. So I remind you this. Let me see if I can write, and it is okay. I can write. So A is K-linear. Okay.
Mm-hmm.
So we should ask that the ohms of dB of A for X and Y, sorry, for X and Y objects in DB of A, okay, this should be a module of finite length. Okay, I don't know if you know what a module of finite length is, but
yeah, I think we can. Yeah, I think we can assume that people will know that.
Okay.
Yeah.
Actually, we can also require it only for X1, XY. And I will also say that you just need to ask for X1 of XY to be an Artinian module.
Yeah.
So that is nice enough. And also, you have another way to do so, and it is linked to this. So if you have that A not only has enough projectives, but the resolutions are of finite length, then you have that this the bounded homotopy category of complexes over the projectives is actually equivalent to the bounded derived category of A. And then you can prove that it has strongly unique enhancement if and only if the standardness, because you can move to case standardness. So these are the two cases I know.
Okay.
You're welcome.
Okay.
Thank you for the nice question.
Yes. Okay. Is that a pun on nice? No, because anyway. So can you go back to, this is my question, by the way, can you go back to the slide where you were talking about questions on enhancements? And there were a couple of yeses and there was one we do not know.
Oh, yes. This one?
Yeah.
The first one?
No, the third one. I want the third one.
Oh, the third one is we do not know. Yeah.
Okay, so I'm guessing you know examples of triangulated categories that do not have strongly unique enhancements.
Well, if you have algebraic triangulated categories with a non-unique enhancement, then they of course do not have a strongly unique enhancement. Simply because.
Right. Yeah. Okay. Yeah. No, go on.
Go on.
No, I mean, you were saying something. Sorry, interrupted you.
Yeah, well, that actually follows from the definition, because if you think about it, if you have two enhancements, C, E, and C prime, E prime, we have a zigzag of quasi-equivalences. And now you can just stop here, because this is all you need for uniqueness of enhancements. So strongly unique enhancements always have, if you have strong uniqueness, then you have uniqueness.
Yeah, so I mean, you mentioned the paper by Strickland, Schwede, and Fernando Muro.
Yes.
And I believe they showed in that paper that there are examples of triangulated categories that are neither algebraic nor topological.
Yes.
And from your talk, I'm guessing like this theory of strong unique, or was it semi-strongly, this strong unique enhancements. I mean, this theory, as of now, does not apply to topological triangulated categories. Is that right?
I do not know enough about topological triangulated categories. I don't think there's a definition of strongly unique enhancements in that case, but maybe I'm mistaken. I've only seen this definition to apply to algebraic triangulated categories. Okay.
Yeah. Okay. Do we have any more questions for Antonio? No? All right. So in that case, let's thank the speaker again. Yeah, I'm guessing people are clapping in some other way today. So next week we have a talk by Andrew Baker from the University of Glasgow. We don't yet have a confirmed speaker for the week after that. So if any of you want to speak, please get in touch. Okay, thank you all of you again. I hope to see you all soon. And thank you again, Antonio.
Thank you.
Thank you.
Okay.
Thank you.
Bye.
Bye.